start our morning session. We're very happy to have Vivek Shende, who is going to talk about quantum mirror symmetry from Conifold.
Well, thanks, Tony. I'm happy to be here in Miami. I live in usually Denmark now, which is a bit colder, so it's good to get some sun. So I wanted to talk about some work I've been doing with Tobias Ekholm. And this work is I think we did it last year or so, but well, there was no conferences for a while, so I'll talk about it now. So I have to review what I said last time I was here in Miami, which is about Gromov-Witten theory and open Gromov-Witten theory. So let me just briefly recall that to define Gromov-Witten theory in Calabi-Yau threefold, very roughly speaking, you consider moduli of holomorphic maps. It's compact, virtual dimension 0, and so you want to perturb and then count points. And then the main thing that you have to think about is whether your perturbation does or whether your count does or does not depend on your perturbation. And the way you think about that question is you connect your perturbations by some family of perturbations. And the reason why in the end it won't matter how you perturbed is that, degenerations of closed holomorphic curve have codimension 2, and so you never see them. And that means that in this path, you have some kind of nice cobordism between solutions. So that's about the usual story of Gromov-Witten invariants, and I want to discuss open Gromov-Witten invariants. Now, with open Gromov-Witten invariants, you meet various problems, and the sort of problem that you meet is that as you vary in moduli, you encounter degenerations in codimension 1. And the kind of degeneration that you might encounter, I mean, there's here's one that somehow you might find particularly worrisome. You have this kind of curve, and you have some path on this curve, some path on this curve, which gets contracted to a 0 length. So this curve, it might degenerate into someone who looks like this. And if this kind of thing happens, then your family just stops in moduli. You find the boundary. And that means that the boundary of a one-parameter moduli space, well, it has components at the beginning, components at the end, but also can have components in the middle, which means that your count of curves is not a priori well defined. Okay, so that's the basic problem with open Gromov-Witten theory or any kind of holomorphic curve with boundary counting. So people try and deal with this in various ways. There's the work of Fukaya and company on somehow for Lagrangian Floer theory and Gromov-Witten theory, and like bubbling and so on. But there's always some kind of difficulty. On the other hand, for a long time, people have believed that there are open Gromov-Witten invariants. The physicists, they say that not only do they exist, they predict what their values are. And sometimes it's even possible to calculate. I think Melissa calculated some, and other people calculated some. And however, these calculations, the nature of them is that there's not somehow a general definition of open Gromov-Witten invariance, but maybe in the presence of S1 action or a complex conjugation or something, which somehow prevents this kind of prevents you from going to the boundary of the moduli space. And it wasn't some kind of general definition, but there was an important an important idea from the string literature, which is that somehow open Gromov-Witten theory, it had to have something to do with, at least in 3 dimensions, with Chern-Simons theory on the Lagrangian brane. And let me just say one word about what that idea of Witten was. The idea is that, well, he was studying open strings, and if you have open strings that stay very close to the Lagrangian, in the open string field theory, there's basically one interaction term, and that interaction term turns a string like this into 2 strings. Looks like this. And the relevant part of that for the discussion at hand is that whatever that interaction term is, it has it involves 3 things. And so some kind of cubic term. And that cubic term, when you have many Lagrangians somehow living next to each other, well, it's, if you have n Lagrangians, strings stretching from one to another, there's n squared ways to do that. And this cubic term is some like cubic term on matrices of size n by n. And that starts to look something like Chern-Simons. So that's more or less how Witten arrived at this idea that open Gromov-Witten invariants should have something to do with Chern-Simons theory. And this idea was sharpened over time. Aganagic-Vafa made some particular conjecture about some setup in which the open Gromov-Witten invariants should be exactly equal to certain not invariants called colored HOMFLY polynomial. Last time when I was here, I discussed a proof of this conjecture in the special case when there was no color. So this was last time without color. And this time, maybe I will explain how to put the colors back. Okay, so I have to say, with that preface, I have to say some things about knots. Well, here are some knots. And the item I should introduce is something called Skein module. And Skein module, it's something you can associate to a 3 manifold. It should be oriented 3 manifold. And you ask over some polynomial ring, you take the free module generated by all links in your 3 manifold. They should be framed links. And then you impose these relations. There's 3 of them. And the first theorem in the subject, due to these HOMFLYPT people, that's 8 people, is that the skein of essentially what they did is they calculated the Skein module for the 3 sphere. And the result is that the Skein module for the 3 sphere is free, generated by the class of the empty link. And what that means is that you can define a knot polynomial by a knot invariant by saying you take any knot or link, you express it as, it's an element in the rank 1 free module over the empty link, and you compute the coefficient. So that's what the HOMFLY polynomial is defined to be.
Are there relations in this freely generated?
What?
Is it freely generated?
It's freely generated by framed links modulo these relations that I wrote. And in case it's not clear, the meaning of these relations is that if you have 3 knots or links which look the same everywhere outside a small ball, and in the small ball they are related in this way, then the elements in the Skein module should satisfy that relation. Well, that's for the first one. The second relation is simpler. It says that the unknot is just equal to some particular value. And what those third relation says is that, I said framed links. I didn't say what framing was. Framing is you should choose a normal vector to link. And when you draw a picture like this, the normal vector is understood to be pointing out of the blackboard. And so in that third line, you can convince yourself that, well, the normal vector on one side is winding around once more than on the other side. And so that third equation says that if you want to change the framing, you are free to do so at the cost of the A, adding or removing an A. Okay. So that's the Skein module. And so what I was explaining last time I was here is the existence of this Skein-valued open Gromov-Witten invariant. And well, there's a number of things happening in here. So let me, in this formula, so let me explain them. Well, the first thing to discuss is this word bare. Bare means that, like when you count Gromov-Witten invariants, usually you allow all holomorphic maps. And I am only going to allow some holomorphic maps, namely those which do not collapse any component of the curve. Now, this should worry you. It should worry you because, well, the reason why counting is usually well defined is that there's Gromov compactness theorem, and Gromov compactness theorem, well, it applies when you count all holomorphic maps. That space is supposed to be compact. But here I've said I'm going to throw away some part of the moduli space, and so you should be concerned that what is left may not be compact. And then there's a worse problem when you vary in families, that somehow some families may just vanish due to this piece I've thrown away. And so in order to explain why it's legitimate to do this, one needs to prove a theorem that is slightly stronger than the Gromov compactness theorem, which shows that if you have a limit of this kind of bare holomorphic curve, and the limit develops a ghost bubble, then the non-ghost part of this limit has to be singular. So this is a true theorem, one can prove it. But the significance of that theorem is then if you've inductively set up perturbations, you can ensure in this Calabi-Yau setting that no image of bare curve is ever singular. And so you rule out this kind of degeneration. Okay, so I don't want to discuss this kind of technical aspect today, but I just mention it because it is important.
So the variable Z is variable, or is it?
You remember here there was a Z already, and it's that Z. Okay, but I'm going to go through and explain these things term by term. So I have a sum over moduli spaces, other characteristic, and so on. And so each curve, I count it in some way. And okay, first of all, it's in some moduli space. This kind of stuff may have orbifold weights and so on. That's this weight U. It's just the you have a curve. It comes with some weight. Then this Z to the minus Euler characteristic. That's rather than count, I should say, I count disconnected curves, and rather than count by genus, I count by Euler characteristic. So that's the Z variable. Then I record, like when you do closed Gromov-Witten theory, you should record homology class of your curve, and I record that in this Q power. Now the most unusual, one unusual aspect of this is this A variable. What is this? Morally, it's supposed to be a linking number. It's a linking number of the curve with the Lagrangian. And in closed Gromov-Witten theory, that would make good sense. You can, curve in CY threefold is two-dimensional, Lagrangian is three-dimensional, should be a linking number. To define linking number, of course, you should choose bounding chain for the Lagrangian. That's what it means to give a linking number. What's or is it maybe co-bounding chain? Anyway, so what's here is, but what about an open curve? Well, this curve ends on the Lagrangian, so you might be slightly worried about how could you define a linking number. So that's a thing. Maybe I won't explain it now. I just tell you should be worried about it, and then you can ask me about it some other time. And finally, there is this maybe most unusual part, which is I count the curve not by a number, but by its boundary viewed, its boundary is a knot. I mean, it's a collection of circles and Lagrangian. I view it as a knot, and then I say, okay, this is an element of the Skein module. That's what's happening. So let me explain to you how the proof of this theorem works. The idea is that I have to study all the degenerations which happen in moduli space, well, how does it work? So this picture is maybe not so enlightening. So let me draw it a bit better. This top row is one family of curves, and their the boundary. Here's one example of this family. I have some kind of the boundaries of these curves is what I'm drawing, and this this one has boundary 2 circles. Okay, and then you should imagine that there's a cylinder which goes. So the place I'm drawing the picture is the Lagrangian, and then off going in some other directions is some cylinder. And so okay, so you have this kind of curves. And maybe I'll draw in a different color. Maybe I won't try and draw the Lagrangian, the curve which is coming off. And the point is that at this moment, so this is a cylinder, and at the generic moment, it's an embedded cylinder. But at this special moment, it's an immersed cylinder. At this immersed moment, you can do some kind of whatever Fleur gluing or whatever it's called of this curve, and you find a smooth curve. And since you've glued it, it was before an immersed cylinder, and now it's become an embedded genus 1 curve. So if I were to draw what's going on here, I guess it would look like in the boundary. I mean, its boundary would look like before, like something like this. But then somehow you have created some genus in this. Okay, so that's I don't know if that makes the picture any more enlightening, but that's what's supposed to be happening. And the observation is that whenever this kind of singular moment happens in moduli, it happens in somehow 2 ways. And well, this picture, it illustrates that you might have thought that there was a problem because there's one curve on one side and 2 curves on the other, but it also explains the solution to that problem, which is you just declare that 1 equals 2, which might be concerning, but it becomes less concerning when you declare it in the Skein module, because that's nothing other than the Skein, one of the Skein relations. So this is supposed to show you that's well-defined way to count. And that's not the only kind of degeneration which can happen. There's another kind of degeneration where a curve, it somehow has a boundary on the Lagrangian, and that boundary collapses to a point. But at the same moment when that degeneration is happening, there's a different thing which has happened, which is you have a curve of 1 genus less who has accidentally touched that Lagrangian at a point, and you know, in a family which is just passing through. And this okay, you should also declare that one side equals the other side, and declaring that involves, again, this kind of Skein relation. I now have to explain to you, so I didn't have to explain to you about the Z before, because Z was just counting genus or Euler characteristic, and you gained or lost an Euler characteristic when you did this gluing. So that's why the Z before. Now I have to explain to you a bit about this A, which maybe I won't explain so much about. About this A, it has to do with maybe there's not so much to say. I mean, A was about linking number, and if you have a sphere which has passed, you know, like if you have two knots and you pass that one through each other exactly once, then you've changed the linking number. And here I'm like counting linking number multiplied by 2, and so I change the linking number by a squared, you know, by 2, and you pass the curve through the Lagrange. Okay, so that's the proof of this theorem. It's a bit longer when you have to read it. And then the other thing I explained last time was that using this theorem, you can prove this Aganagic-Vafa conjecture. And well, this is the statement of the Aganagic-Vafa conjecture, and the proof of the Aganagic-Vafa conjecture about this knots and conormals and HOMFLY. So okay, maybe I'll just tell you what the conjecture said. It says if you take a knot conormal and you push it off the 0 section in the cotangent bundle to the 3 sphere, and then you follow it across what's called Conifold transition, now you have a Lagrangian in the resolved Conifold, and you can compute its open Gromov-Witten invariance. And the Aganagic-Vafa conjecture is that that computation, the result of it is nothing other than the HOMFLY polynomial of K. Okay, that's what they said. And this is the proof. The proof is, okay, in this cotangent bundle of S3, you push off a little bit this Lagrangian. And when you push off just a little bit, it's not difficult to see. There's exactly one curve, which is this annulus. It's the annulus. So originally the conormal to the knot, it meets the 0 section in the knot. And if you push it off, then that knot traces out an annulus. You set things up correctly, that annulus is holomorphic and the only one. So the count of curves is one curve. But you have to remember how we count the curve. We count it by its boundary. And the boundary of that curve in S3 is nothing other than the knot itself. So it's the class of the knot in the Skein module. So when we pushed off a little bit, you get the HOMFLY polynomial in a stupid way, more or less by definition. But then you push more, or you precisely do some kind of SFT stretching near the 0 section. And what happens on this degeneration is that, well, when you do this SFT stretching, you can get these kind of broken, buildings, except those buildings, they have to break along index 0 Rabe orbits. And S3 has no index 0 Rabe orbits. It has to do with the fact that it's round. And therefore, the curves cannot break. And so they all have to be in the outside. They can't be in the inside because cotangent bundle of S3 is exact. So they all have to be in the outside. And now you have an interesting curve count. But by invariance, the count before, which was the class of the knot in the skein, equals the count after, which is some interesting count. But this interesting count, all those curves had no boundary in the S3. And so we have this formula that says the class of the knot before is some count, which is a mystery, times the class of the empty knot. But you recall now the definition of the HOMFLY polynomial, which says whatever that thing is the HOMFLY polynomial. Okay, so that's the proof of the uncolored version of Aganagic-Vafa conjecture. So this is what I explained last time, and I somehow apologize to everyone who was here last time and has too good of a memory. I had to review this. So now I move on to new things. And what I would like to discuss now is we will study not just, so remember the setup is that I have, for example, the conormal to the unknot in cotangent bundle of S3, and that's a Lagrangian which goes to infinity. Okay, it's non-compact. Before, I was just studying holomorphic curves, which are somehow compact and end on it on the inside. And now I want to contemplate also holomorphic curves which may possibly be asymptotic to Rabe orbits at infinity, or Rabe chords at infinity. And the reason I want to do this is that I want to find some positive dimensional moduli spaces. So in the Calabi-Yau setting, all moduli spaces of compact curves, those all have dimension 0. But if you allow this kind of asymptotics at infinity, the index of the appropriate the appropriate PDE, it has some contributions from this behavior at infinity, and so you can find positive dimensional moduli spaces. And the reason which we want to find positive dimensional moduli spaces is that a zero-dimensional moduli space gives you a number. A one-dimensional moduli space, well, if you think about its boundary has to be 0 in homology, because that's how boundaries work. And therefore, it gives you a relation between two numbers. So you can learn equations by contemplating one-dimensional moduli spaces. So that's why we want to do it. I just mentioned, so now if you imagine I have a one-dimensional moduli space, I should account to you about what kind of boundary it has. And there's two sources of boundary. Okay, one source of boundary is that we already discussed it. That you can have this kind of boundary breaking or bubbling of the holomorphic curve. We already discussed that. But there's a new source of boundary, which is this kind of SFT degeneration at infinity. And I don't know what these pictures are. These kind of, I guess these are pictures of curves that live at infinity. So what is it? What does it mean at infinity? When you do this, when you study this kind of SFT, you have maybe some Lagrangian. This is Lagrangian, and in one parameter family, the kind of degeneration which you can imagine happening, you understand them by you make as kind of cylinders. This is boundary of L times I, and the kind of thing to which you're supposed to understand that a holomorphic curve can degenerate into, it looks like this kind of thing. Maybe somehow it has some Rabe chord asymptotics, has maybe some behavior, and it has some behavior in the I mean, it is what it is. Okay, some kind of curve. This is the kind of picture which you're supposed to contemplate. It's kind of curve which has, in general, many levels, and something in each level. Okay, so we should think about this kind of degeneration, and the point is that one of those kinds of boundary we have already, if we count in the skein, count curves valued in the skein, it's invisible to us, this kind of boundary breaking. Because I already explained to you that in one parameter family, if all that's happening is kind of boundary breaking, Skein value count is invariant. So the only thing left is this SFT degeneration where it breaks at infinity. Now I want to, the example I want to discuss today is an example of where the simplest possible behavior happens. And the simplest possible behavior is when this Lagrange, at infinity, this Lagrangian in its boundary, there's only Rabe chords of index. Maybe I should say, what is Rabe chord? Rabe chord is a trajectory of the Rabe vector. If you have a contact manifold, there's Rabe vector with a fixed contact form, there's Rabe vector field, and Rabe chord is a trajectory of this Rabe vector field. It goes from L to itself. Anyway, so if you have, now maybe I also say, okay, why do we discuss having Rabe chord asymptotics? The point is that usually we demand that the complex structure should be conic in this conic in this end. And if you have a complex structure that's conic in this end, and you have any kind of curve with boundary in the Lagrangian, it necessarily goes to this kind of coordinate. Okay, so if you have these Rabe chords, and if they all have index at least 1, then if you ask how these curves can break in one parameter family, well, by somehow dimension count, there's only one possible way. Okay, and the only possible way is you have some curves out at infinity in this cylinder, and then you have some curves in the interior, and moreover, there is no none of these curves go to these Rabe chords. Why do they not go to these Rabe chords? Well, if I allowed curves going to these Rabe chords of positive index inside here, the dimension of that family is like negative or something, and so it shouldn't exist in maybe 0. Anyway, it has the wrong dimension to exist. So what does that mean? It means that when we study the boundary, which means we count these SFT degenerations, and the boundary is 0. So in other words, the count of all these 2-level SFT curve counts 0. But what is that? Well, I just said that such counts, there's somehow disjoint counts of curves off in the symplectization and curves in the interior. And saying there's disjoint curves means I count the ones on the outside, that makes some big series. I count the ones on the inside, that makes some big series. And I count disconnected curves, so the count of all curves is the product of those 2 series. Okay, so that says that I have 2 series and their product is 0. That's the relation which comes from contemplating this one-dimensional moduli space. Now, you might at first be a bit worried about, I've said I have 2 counts, they're presumably themselves not 0, and their product is 0. But you have to understand where I was doing this count. I was doing this count valued in the Skein. And as I'll explain in a second, this Skein, it's not like a space of functions. It's going to be some kind of non-commutative algebra. So this equation is true, but it's true in the Skein, and that is going to amount to a certain operator equation. Okay, so let me explain now how to understand this kind of equation A psi equals 0. So we have to discuss again Skein modules and so on. So the first thing to note is that if you have a surface, then you study Skein module of surface times an interval. And that's a non-commutative, in general, non-commutative ring. And how is it a ring? Well, you take the surface times the interval and you stack it on top of the surface times the interval. You glue the intervals together, and you get a surface times an interval. So that's some kind of action. And a similar thing, if you take a circle times a disk, that's another kind of 3-manifold. And the Skein module of that is a commutative ring. And if you ever thought, the reason is the same that, pi 2 is commutative, or that if you ever contemplate little disk operad or E2 operad or whatever, that's commutative. The operation is if you take 2 disks, you stick them together, but you can roll the disk around the disk to the other side. And so you see it commutes. Okay, and then if you have a 3-manifold with boundary, the Skein associated to the boundary acts on the Skein of the 3-manifold. You just stick a copy of surface times interval at the boundary. Okay, so summing up these discussions, well, if you have in particular, we see that there's an action of some presumably non-commutative algebra given by the Skein of a 2 torus times an interval on whatever the underlying vector space is of some commutative algebra given by the Skein of a solid torus. So this was just somehow a general contemplation about skeins. But for this to be useful for us, I had better tell you what is this algebra and how to calculate with it. So fortunately, this has been computed, I think, starting with derive. And the result is that the HOMFLY skein of the solid torus, it's roughly speaking, it's indexed by pairs, has a basis indexed by pairs of partitions. We're only going to look at somehow single partitions. It's generated by knots which somehow wind around this torus and going positively, and knots which wind around the torus going negatively. We're only going to be interested in the ones winding positively. That piece of the skein is the same as a somehow has a basis given by partitions, and its multiplication is somehow the same as the ring of symmetric functions. So that's how that works. And then there's I said this kind of torus times interval acts on the solid torus. And the way in which it acts, so first of all, the torus times the interval, it's kind of its skein is kind of interesting algebra. And what that algebra is, there's some algebra called elliptic Hall algebra. It's an algebra which has two variables, q and t. And there's a kind of the stupidest specialization of this algebra is when you set q equals t. I guess that's not the stupidest one, but that's a specialization. And the result of Morton and Samuelson is that that is the skein algebra of this kind of torus times interval. And they also give you a formula for how this algebra acts. There's a standard algebra of elliptic Hall algebra on symmetric functions, and they prove that this action is that action. But let me just write the two formulas which somehow contain all the information. So I should say what these P01 and P10 are. So on the torus, you can draw a circle, for any rational number P over Q, you can draw the circle of slope P over Q. And P10 means the circle with slope 1, and P01 means the circle with slope infinity or something. Maybe the other way around. P01 is going to be, in this action, it will be the one which is contracted in the solid torus. So I guess that's the meridian. So anyway, the result of these guys is that if you look at the action of P01, it's diagonalizable. And moreover, its eigenvalues, the eigenspaces are non-degenerate. So this element P01, somehow it's very important. Oh, sorry, P10. This element P10 is very important to this whole story because it somehow it tells you a natural basis for the skein of the torus. And in terms of this somehow symmetric algebra, symmetric function theory and elliptic Hall algebra and so on, what that basis is it's the Schur basis. Okay, and so then this P01, they also compute what it does. It's the operator which adds one box, and that has some representation theoretic meaning, which I won't discuss. Yeah, so these are the formulas which are important to know. And so now let's discuss this case of the unknot conormal. Okay, so the unknot, it's a true fact for the unknot conormal that there are only Rave chords of index at least one. So we're in this simplest possible situation that I mentioned before. And now we want to count the curves at infinity. So how to count them? Well, one way is you look at the map which takes the contact sphere at infinity, and there's an S1 action. You take the quotient by the S1 action. That gives you a map to P1 times P1. And it turns out this conormal, the Legendrian at infinity, it gets mapped to the torus, which sits at the center of the moment map image. And that's one of many ways you can count the holomorphic curves. And if you do it, the virtue of doing it this way is that you see from the picture that there are 4 holomorphic curves. Okay, and that's it. Then you have to work a little bit harder. I said you have to count their boundaries in the skein, and you have to work a little bit harder to figure out what their boundaries are, not very much harder. This formula I've written here, well, it has 4 terms because there are 4 curves, and well, then you have to think about their boundaries. You might ask, you might complain that this picture I've drawn is very symmetric and the formula is not completely symmetric. The source of the asymmetry is that the boundary of such a curve, it is a path on the torus, not a loop, because it has to go. One part of that curve is traveling across a rabecoid, which doesn't live in the torus, and so you have to pick some way of closing up all these paths, and that choice is the source of the asymmetry. I guess there's one other source of asymmetry, which is this bounding for code, this for chain which bounds Lagrangian, which you also have to choose. So that's another source of asymmetry. Okay, but so you got this operator. This is an element in the skein of the torus times an interval. And we had before this equation A psi equals 0. And it's not so difficult. You have to do some combinatorics, but it's not so difficult to convince you. It's almost immediate that it has a unique up to scalar solution. And then it's not so difficult to convince yourself that, well, this is what the solution is. You have to do about half a page of combinatorics. So there's some formula. And this formula, it agrees with calculations people did in the past of what is supposed to be the Gromov-Witten invariance in this situation. Again, those calculations were done in a different formalism, which doesn't have a general somehow definition. And I don't know a theorem, which is a a priori comparison theorem between this setup and the old setups. But anyway, this is to me, the interesting thing here is not the solution to the equation. The interesting thing is that you learn the equation which determines all the Gromov-Witten invariants a priori. Okay. So I want to explain now the title of this talk. The title of this talk was quantum mirror symmetry. And I want to explain in what sense this is a quantum mirror symmetry. So what is mirror symmetry? Well, a mirror is supposed to be moduli space of Lagrangians. Okay, you have some symplectic manifold, and you want to make algebraic variety, and that algebraic variety should be moduli space of Lagrangians. When you have this non-compact setting, you may want to prescribe some information at infinity. And one way to prescribe such information is by naming a Legendrian in the contact boundary. And when you do this, there is some item people study. It's called Chekhov-Alyashberg algebra. And it's made, I think maybe that's supposed to be H lower 2 rather than H upper 2. It's made, you use some homology variables, and then you take algebra generated by rabecoids, and there's a differential. The job of that differential counts curves. And for us, the relevance of this algebra is that if you have a Lagrangian, which this should say, okay, so that's correct. That's correct. So I think this is supposed to be H lower 2. And then this should say L equals lambda. Okay. So when you have a Lagrangian ending on your Legendrian, well, what you get is you get a morphism from this algebra to the complex numbers, and the nature of that morphism, the way you define that morphism is to each RAID chord you assign the count of curves which end on that RAID chord. Okay, so the space of such morphisms. Yes, I think there's another. Yeah, this slide I made last. So this one should have said C is H2. Because you somehow count the. No, I had it right before. In any case, the space of such morphisms you should think of as a mirror, because each Lagrangian with this kind of end, it gives you such a morphism, and then maybe there's more objects in Fukaya category than just honest Lagrangians, so you allow all such morphisms. And this was an idea of Aganagic-Vafa and Vafa. Okay, so in this setting here, well, such a map. What does it mean to have such a map? Well, the only constraint is that D of an index 1 RAID chord had better get sent to 0. Okay, so such maps are the same as taking well, this algebra. Well, in other words, it's a curve, or it's a thing cut out by the disk count, and that count is well known to the and it's the same 4 curves we counted. I mean, by definition, it's the same 4 curves we counted before, except in this this previous theory about not contact homology. You understand that equation as some kind of equation in the commutative place, namely the group ring of this homology. And now we understand it in a different place. We understand it in the Skein module. And so what we learn is that that a priori, the operator which annihilates the Gromov-Witten invariants, its somehow dequantization or whatever, is this what used to be called augmentation polynomial, which you should think of as the equation of the mirror. Okay, so that comes with this package for free. So that's why that's supposed to explain this title, quantum mirror symmetry. So okay, so let me mention some questions. Somehow maybe questions for Melissa. One thing is you can put several Lagrangians. You can do other toric Calabi-Yau threefolds. I expect it works in that generality. It definitely works for C3. I haven't tried to compute. When I say works, I mean the only thing that needs to work is that you need to know that for literally the story I just told to go through without any further difficulties, you need to know that there are only RAID chords of index at least 1. That's the thing which has to be true for it to work. Then here's a remark, which is that when this works, well, all this information of curve count, it was determined by what's happening at the contact boundary. Now you can imagine some particular situation where your Calabi-Yau, toric Calabi-Yau or whatever was given by taking a resolution of a singular Calabi-Yau. Now that resolution happens on the inside. So the equation which determines the curve count does not care what resolution you used. And therefore, people used to, there used to be some kind of question, I don't know, probably resolved by now, but there used to be some kind of question about if different Crepin resolutions of a singularity give the same Gromov-Witten invariance. This implies a priori, the answer is yes, at least for these open curve counts, because, well, the curve count is determined at infinity. Something I don't have a clear idea about how to do. Here, I was only counting curves with boundary. It was disconnected curves, and every component had to have a boundary. And you can ask, is it possible to, by some similar abstract argument, extract a formula for the closed curve count from the open curve count? I don't know how to do that. And here's another interesting question to me is if somehow you can deform these recursions. Why should you think you can deform them? Well, you know, I was discussing Gromov-Witten theory, but in this dimension, it's supposed to be the same as Donaldson-Thomas theory, and that is supposed to have a deformation, given either by this Kuhn-Nekrasov story or some motivic stuff, or. And you can ask, so I wouldn't know how to derive a priori a T deformation of these recursions, but you can ask if they admit a T deformation, which will then, you know, perhaps annihilate this T deformed, this refined DT theory. And it's natural to expect this because, as I mentioned, the place where this relation lives is in the Skein module of the torus, which does admit a natural T deformation to elliptic Hall algebra. And in fact, it is true that at least for the Conifold in C3, such a deformation of the operator does exist, which annihilates the desired series. And finally, in the past, when people have studied this kind of Gromov-Witten theory question, often they study it in the context of topological recursion. I don't really know what is topological recursion, but one could, it seems natural to inquire whether the discussion here is in some way related. Okay, so I have a few minutes left, so I will explain now how you prove this Aganagic-Vafa conjecture with all colors. So let me explain how they thought about it. Okay, so the point is, maybe you know that the cylinder. They thought, and by now we know in mathematics that like a single covered cylinder, it corresponds to introducing the Wilson line into the Chern-Simons theory of its boundary. That's what. And what Aganagic-Vafa, basically their argument was, well, if you do a multiply covered cylinder, then it had better introduce the Wilson line, which you know, it just goes n times around that boundary. And that Wilson line is trace of the nth power of the holonomy that has some expressions, and you know, you can use representation theory to expand that in another way. But this was the core of their argument, this fact here, this observation here. I mean, this is the part of their argument which explains how to go from uncolored HOMFLY to colored HOMFLY. So if I know this fact in mathematics, if I know how the multiply covered cylinder contributes, then that's all I need to know to upgrade their argument. I mean, to upgrade from usual HOMFLY to colored HOMFLY. Okay, so I have to figure out how the multiply covered cylinder contributes. And so just translating from this Wilson line, translating from the basis in traces of powers of the holonomy to this Schur basis, you get this prediction. And as I promised you, I will explain to you now why it is true. So I have to somehow study a multiply covered cylinder. And the point is that I can basically study it anywhere. I have to just go somewhere in some geometry and find some multiply covered cylinder. The simplest place you can ever find this is you take cotangent to solid torus, and you take a conormal to the longitude, and you push the conormal of the longitude off the zero section. As we were discussing before, this traces out a single annulus, and the total contribution should be the count of just this annulus. The reason why I want it in torus times torus has to do with the nature of the operator I'm looking for. I'm looking for an operator in skein of torus times skein of torus. Okay, so this is the correct place to study it. But if you think about what that geometry is, well, what that geometry is it's you take like the axes in C2 and you multiply it by a circle. And the axes in C2 at infinity, that's the Legendrian HOMFLYPT. I guess you have to put the appropriate symplectic form. And the Legendrian HOMFLYPT, we've studied it forever. So we know everything there is to know about its holomorphic curve theory. And adding this extra T star S1 factor, it makes it some more spot situation, and so it's perturb out, it's fine. Anyway, what you learn from if you go and look up holomorphic curves for the HOMFLYPT, you immediately learn that the curve count at infinity is given to you by this operator. And this operator, well, this P10 is, I told you it was diagonalizable with non-degenerate eigenspaces, and it follows immediately that anything annihilated by this operator must be diagonal, because if I act in the first factor, this operator is somehow like A tensor 1 minus 1 tensor A, and so the action on the first factor has to produce the same eigenvalue as the action on the second factor. So it's diagonal, has some coefficients. Those coefficients, just from looking at this operator, are a mystery. But we have already done one calculation, namely we calculated the unknot. And it turns out the unknot is enough to pin down the value of all these coefficients. They're all 1. And that's it. So I learned that the contribution of a multiply covered cylinder is given by this this formula, which is the translation of this Aganagic-Vafa prediction. Okay, I think that's all I had to say.
Thank you. Any questions?
So Vivek, I somehow missed why did you say something about elliptic Hall algebra and its action? It appeared on one slide, but it did not appear after that.
I had to understand in what sense this equation, and then the later one for the I had to understand what this equation meant and how to solve it, right? And so where is this equation? This equation, this thing is in skein of T2 times I, which is this elliptic Hall at Q equals T.
You specialized. Okay.
And this thing lives in the symmetric functions. Okay, so now here, of course, it was not important that you knew it was the elliptic Hall algebra. It's just important that you knew somehow how to compute in this algebra. The relevance of it being the elliptic Hall algebra, its fancy name, but the relevance of that is that I can then pose this question. because I can ask, if you deform out from this Q equals T, what happens to the solutions to the equation? So that's one reason why I said it.
Yeah, because kind of mechanically it's not difficult to understand, at least for torus knots and the conifold, the T deformations more or less straightforward. Yeah.
Well,
But
I think the T deformation of the solution is straightforward. I
yeah,
don't know if the T deformation of the recursion is known.
yeah. I mean the solution. Yeah. All right. Thank you.
I think Melissa has a question.
Oh, yeah, so when you know the recursion has a natural T deformation, does this have something to do with what the
I don't know when the recursion should have a natural T deformation. You might imagine that there's this refined Chern-Simons story of Mina, and that has something to do with circle actions. And so you might imagine that it's related to some existence of circle action.
Other question? Okay, thanks, Vivek, for the very nice talk.